19.1 is about the standard electrode potentials, looking more at what's happening in voltaic cells and the actual amount of voltage that can occur due to redox reactions. This will be a long lecture, so pause as needed or fast forward. Before we begin, there's some basic units and terms that are associated with reduction and oxidation reactions and just electricity in general that you need to be aware of. First, the amp, or capital A, is the SI unit, which is the International Standard Unit for electric current, which is also symboled as I. A coulomb is capital C, is the SI unit for electric charge, also written as Q. Therefore, we could have Q equals I times T. This is the amount of charge transported in 1 second by 1 amp. An easier way to remember this is C equals A times second. So those are the actual units. So coulombs equals amps times seconds, and looking at the amount of charge that is received from current over time. One electron has a value of 1.602 times 10 to the negative coulombs. 1 mole of electrons has 96,485 coulombs per mole. This is also known as Faraday's constant. Faraday is the scientist that was researching redox reactions and came up with a coulomb and, of course, the transfer of 1 mole of electrons and how much energy comes from that 1 mole of electrons. Volt is also capital V, is the SI unit for the potential difference within a voltage or a voltaic cell. The equation we can use for this is volts equals joules times coulombs to the negative 1. That is the amount of energy per coulomb. The electromagnetic force, or EMF, is the greatest potential difference a cell can make. It is measured in volts. This is essentially what we'll be looking at, which is called cell potential, or E cell. And that is how we measure and go through and determine what each cell, or the amount of energy an oxidation or reduction reaction can have in comparison to each other. So now the thing is, when we go through and look at how much energy a voltaic cell can have, we have to make comparisons of half-cell electrode potentials, but we need a reference point for that to occur with. Alright, so what do? So we're looking at our EMF, which is the electromotive force. This is created as electrons flow from the anode cell, the negative voltaic cell, to the positive cell, or the positive voltaic cell. So we go from the anode to the cathode. Now the differences in their electron or electrode potential gives you the magnitude of the voltage. Where do we get these values from? Well, they essentially come from a list of your relative reducing powers, which we had learned about back in 9.3. Now, how do we actually determine these values? We need that reference point. Therefore, they created a standard hydrogen electrode. So hydrogen became our standard point that we set as an arbitrary value of 0 and went from there. Alright, so here's the setup of what happened, or what happens to create your standard electrode potential. So we have a half voltaic cell created. In the beaker we have an acid solution. There's 1 mole per decimeter cubed of aqueous hydrogen ions from that acid solution. And this solution has a pH of 0, which means we can assume full dissociation of our acid. Therefore, we are only able to look at the hydrogen ions. Submerged, we have a platinum electrode. The platinum electrode is a very inert metal and acts as a catalyst for the proton or hydrogen reduction. Because hydrogen does not have a solid pure metal, we can use platinum in its place. Then we have this glass tube. This glass tube that's submerged within the acid solution allows for the collection of hydrogen gas, but it does have holes within the tube so that the hydrogen gas can escape back into solution so that we can go back and forth between our oxidation reduction. But we need hydrogen gas to go in first. So as we have our hydrogen ions, we also pump hydrogen gas at 290 Kelvin and 101 kilopascals into that glass tube to take part in the redox reaction. So as we immerse the platinum electrode, the following equation happens, or reaction. We have two protons in their aqueous form react with two electrons to make hydrogen gas. Looking at the way in which this is written, those protons are being reduced and the hydrogen is being oxidized. Therefore, this can occur as an equilibrium reaction because we're not set up as a full voltaic cell. And so the equilibrium reaction will take place between the two. Now, the value in which this takes place is arbitrarily assigned a 0 value. Therefore, when we connect this half cell to any other half cell with the voltmeter hooked up and your salt bridge, the whole shebang, you will see any difference in voltage read by the voltmeter belongs to the cell in which we had attached, because we're assuming that hydrogen has a value of 0, and therefore every other cell, the reading belongs to that particular cell. And we'll look at an example of what this looks like. So how do we actually go through and measure the standard electrode potentials? Well, they must occur under standard conditions, therefore create what we call standard half cells. In these standard half cells, the concentration of your aqueous solution needs to be 1.0 moles per decimeter cubed. The half cells need to be exposed to 101 kilopascal pressure. It needs to be made up of a pure substance. The temperature needs to be controlled at 298 Kelvin. And if that particular element that we're looking at for the half cell does not have a solid metal that we could use as its electrode, then platinum can be used just like we did in hydrogen. So essentially what this looks like, we have our standard hydrogen electrode, and then we have our standard half cell of another element that we are looking at. We create that external circuit with the voltmeter and salt bridge, so now we have a complete circuit for our voltaic cell. An EMF is going to be generated, and that is going to create what we are looking for, which is this value right here. This is our standard electron potential. That theta sign by the E means it's run under standard conditions, just like we saw in energetics with topic 5. And then the capital E is that electrode potential that each element has been found to have. Alright, so here's an example of how they can do this. We have our standard electrode potential for copper 2+. So here we have copper 2+ and copper solid. In its half cell, we have gone through and determined that it has a positive 0.34 volts. So that is its E theta value. What does this mean? This positive sign means that it has a greater tendency to be reduced because it is above 0. Therefore, the hydrogen half cell becomes oxidized and the copper half cell becomes reduced. Below that, you see our equation, where we have the proper equation for what would happen or what could represent the voltaic cell that is being run here. So since copper is being reduced and hydrogen is being oxidized, you can see from the reaction we have copper 2+ aqueous reacts with our hydrogen gas. Copper is going to take the electrons from hydrogen and be reduced, and hydrogen is going to be oxidized. So now we're going to have two hydrogen ions that are turned aqueous, and we're going to have a copper solid. Again, some things we can look for, as we discussed back in 9.3 and 9.4, is in the copper cell, we would see that copper has been precipitated onto its electrode metal, and therefore, there's less of a blue solution from the copper ion that was in solution. In addition, if this happened to be in reverse, we'd expect more hydrogen gas to have been made, but the hydrogen gas is being used into those hydrogen ions. So we could also test for a pH change as well that is occurring because more ions are being made. So that's a positive value. So therefore, if there was a negative E value, that means that element has a greater tendency to be oxidized, and hydrogen, therefore, is going to be reduced. A shorthand representation of what this could look like. So instead of having to draw the entire voltaic cell, this is a very shorthand version. So we have H2 gas with a phase boundary, which is a vertical line with H plus aqueous. This is our anode, so this is where oxidation is occurring. Therefore, we are going from an H2 to an H plus through the reaction. We use the two dotted vertical lines to represent the salt bridge. And then in the other cell, we have copper 2 plus aqueous with our solid phase boundary line and create copper solid. Again, this is the order in which needs to occur because this is our cathode and copper is being reduced. So this is representing the order of electron flow. So standard reduction potential, actually specifically looking at E theta. You can find a series or a table 14 in your data booklet that provides for a set of given values. Things that you need to keep in mind while you're reading these values from table 14 is all the E theta values are representing the reduction reaction itself. So therefore, if you were wanting to find the standard reduction potential value for the oxidation reaction, it is equal but opposite. So you change the sign to the opposite sign, but the value stays the same. Keep in mind that the standard reduction potential does not depend on the number of electrons. So it does not have to be scaled for the stoichiometric equation present. And then the more positive E theta value, the more readily reduced the reaction or the element is going to be. Alright, so keep in mind, oxidation has the more negative E theta value. That is your anode. The reduction is the more positive E theta value, and that is your cathode. So now we're going to look at a series of ways in which to use these values mathematically and what they represent. First thing, calculating cell potential. This is the one you're going to do the majority of the time. When you're calculating your cell potential, also known as E theta cell, you can calculate the EMF for the voltaic cell, so the electromotive force, or you could deduce the electron flow and predict the outcome of the redox reaction. So here we have the equation which you're going to use. This is the one that you need to remember above all else. We are looking for the total EMF or voltage between the two cells for the entire voltaic cell. This is equal to the E theta value for your reduction cell minus the E theta value for your oxidation cell. Essentially, it's products minus reactants if you're looking at that shorthand presentation. But what you need to keep in mind is all the E theta values must be the reduction values that are provided to you in table 14. So even though you're working with an oxidation cell, and you would think you'd want to turn it to the opposite value, you do not want to do that This calculation is set up to look at all the reduction values, and therefore you want to keep it that way. Also, because we are not looking at the number of moles of electrons that are being moved, we do not need to worry about multiplying this E theta value based on the stoichiometry of the equation itself. Straight up look at what's being reduced, what's being oxidized, and then do reduction minus oxidation from the values you get in table 14. Alright, so an example that we're going to work through. If you have a half cell with zinc and a half cell with copper, determine which one's going to be oxidized and which one's going to be reduced, and calculate your standard electrode potential, or your EMF, for that voltaic reaction. So we have zinc and copper. So I'm going to write the half reaction so I know what it is I'm working with. So zinc 2 plus 2 electrons gives us pure zinc solid. I'm leaving out the states of matter. Then we have copper 2 plus 2 electrons gives us solid copper. We don't know who's being oxidized and who's being reduced unless you go to the reactivity series from 9.3, or you go to table 14 in your data booklet, and you can see that zinc has an E theta value, or an electrode potential difference, of negative 0.76 volts. Copper has a value of positive 0.34 volts. Alright, so now from this we can determine which one's going to be oxidized and which one's going to be reduced, so we could appropriately draw the voltaic cell if we needed to, or do the appropriate calculations. Because zinc has the lower E theta value, that means it's more likely to be oxidized. Copper has the higher E theta value, therefore it's going to be reduced. That means zinc is at our anode and copper is at our cathode. Now that I have determined which one's oxidized and which one is reduced, let's calculate the cell potential difference that is going to occur and what our voltmeter is going to read. So keep in mind that we have E cell equals our reduced cell, so that's copper, minus our oxidized cell, which is zinc. So plug in your values. So we have positive 0.34 minus a negative 0.76, and that is going to give us a value of positive 1.10 volts. That is what our voltmeter would read. So if we were to set up our voltaic cell, everything is appropriate under standard conditions, we would expect to find that the amount of electricity moving between our oxidized cell and our reduced cell should be 1.10 volts. Another way in which we could use all this information and determine what's going on. Alright, so we know that copper solid and silver solid are added to an aqueous solution of copper ions and a silver solution. Alright, so that's all we're given. From here, what we want to do is we just want to write the reduction reactions so that we can go through and identify what their E theta values are. Identify who's being oxidized and who's being reduced. Then you're going to write the half reactions. Then you're going to write a net reaction. And lastly, we're going to determine what the electrode cell potential is in this voltaic cell. So in this particular problem, they're asking you for a variety of information. First thing we're going to do is determine who's being oxidized and who's being reduced so we can write the appropriate half reactions. So copper, 2+, is accepting 2 electrons to make copper solid. If I look in our data booklet, I see that it has an E theta value of 0.34 volts. Silver plus is going to accept 1 electron. And then we have our silver solid. If I look in table 14, it has a value of 0.80 volts. Because copper has the lower value, it's going to be oxidized. Silver has the higher value, so it's going to be reduced. That's the first thing I wanted us to do. Now, write the appropriate half reactions. So looking at copper, copper is being oxidized. Currently, I have it being written as a reduced reaction. So, to correctly show an oxidation of copper, copper is going to be oxidized by losing its 2 electrons. So there's copper's half reaction. Silver is being reduced. So it is actually written correctly as we've already written it. But we have to keep in mind we have to balance the number of electrons between the 2 reactions. And since copper is giving up 2 reactions, the silver needs to accept them. Therefore, we need to have 2 silvers, silver ions, accepting those 2 electrons from copper to make 2 solid silver metals. And there are their half reactions. In 9.2, we had talked about all those multiple steps of writing the appropriate full reaction from a half reaction. We don't have to do that with these 2 because we're looking solely at metal ions and there's no acidic solution taking place, no anions that we have to worry about, so this is just simple ions being transferred between the 2. From here, I want to write our net reaction. What that is going to be is copper solid reacts with 2 silver ions in their aqueous form. This is going to make copper 2+ aqueous and 2 silver solids. The last step that I'd asked you guys to do and calculate was calculate your voltage, or what your EMF would be between your 2 cells. So if we have E cell, silver is being reduced, so I want to use the E value for silver. Copper is being oxidized, so I'm going to use the E value minus the E value for copper. So substitute those values in, 0.80 minus 0.34, and I get a positive 0.46 volts. And so that is what I would expect to see in our voltmeter. The second thing that the second calculation we can use with the standard reduction potential values is determining the spontaneity of a reaction. What we need to do is you want to substitute your E theta values into your E theta cell equation based on the way the reaction is written. Do not change it, just identify what is being oxidized and what is being reduced in the reaction given to you. If the overall value for your E cell is positive, the reaction is spontaneous as written. If your E cell value is negative, it is not spontaneous. Now, for the most part, IB only asks you to determine spontaneity off a positive or negative value. But I have seen ways in which this says, how does delta G relate back to this? Because we talked about delta G in topic 5. And delta G is gives free energy, the amount of energy present for a spontaneous reaction to occur. So now he's talking about spontaneity again. Can delta G come back? Yes, it can. So we can actually calculate the value of delta G outside of a thermodynamic or energetic equation. The way it is used here is delta G equals negative N, which is the moles of electrons being transferred in your reaction, times F, which is Faraday's constant, or your coulombs, for the mole of electrons. So keep in mind that is 96,485. And then E cell is your E cell potential difference. Alright, so an example of how to do this. We are given a reaction where nickel solid reacts with manganese 2+ ion to form nickel 2+ ion and manganese solid. Alright, the question is this reaction spontaneous? So what we want to do is determine which one's being oxidized and which one's being reduced so we know how to appropriately set up our calculation. So here we have nickel at 0, Mn has a +2 oxidation state. This nickel has a +2 oxidation state, and the remaining magnesium has a 0 value. So nickel is going from 0 to +2. Therefore, it is being oxidized. So if I go through and I have Ni 2+ plus its 2 electrons, and we have an Ni, so I know this one's being oxidized. I can look up its E value in table 14 to be negative 0.23. Manganese is going from +2 to 0, so it's gaining 2 electrons, therefore it's being reduced. So Mn plus 2 electrons makes our Mn solid. It's being reduced. Look up in table 14, and we find that its value is negative 1.18. Keep in mind, what I taught you before in the previous examples was the more negative the value, you're going to be oxidized. We're not asking that. What we're asking in this calculation is the way it is currently written, is the reaction spontaneous? So do not change it to make it correct based off what we just did in our last sample. So E cell, we are going with what's being reduced, so that's our manganese, minus what's being oxidized, which is our nickel. Substitute the values, negative 1.18 minus a negative 0.23. We get negative 0.95 volts. This, because of the negative value, is not spontaneous. Therefore, as we could have correctly deduced from the way it was written and the fact that the manganese had an E value lower than that of nickel, we could have predicted that outcome. But the way in which it's written is not spontaneous. Therefore, the reverse reaction would be. Now bringing back the delta G calculation then. So if we have delta G equals negative NFE, we can actually prove that delta G, it is not spontaneous. So the number of moles in which we had of electrons transferred is 2. So I'm going to have negative 2 times Faraday's constant, 96, and I just rounded up to 500, times negative 0.95, and this is going to give you 183,350 joules per mole, because Faraday's constant is joules per volts per mole, and the E value is volts. So volts gets canceled out, leaving us with joules per mole. So this is 183.4 kilojoules. And from what we remember in topic 5, a positive delta G value is not spontaneous. Therefore, once again, another way in which to prove it, and we have that delta G value provided to us, not just the volts. Lots of information we have here. The last example we have is comparing the relative oxidizing and reducing power between the voltaic cells. So this is essentially going back to 9.3 and understanding what's going on with reducing and oxidizing agents. So if we're looking at metals, the lower your E theta value is, the stronger the reducing agent. For nonmetals, the higher your E value is, the stronger the oxidizing agent. Essentially the exact same thing we talked about back in 9.3. So you could go to table 14 and draw in saying an arrow going down the oxidized species, you increase your oxidizing agents. Use an arrow going up your reduced species, you increase the reducing agent, so on and so forth. So what does this mean in terms of an example? All right, so we have potassium permanganate is being reacted with hydrochloric acid. Would we expect chlorine gas to be made during this process? Which would be really good to know because chlorine gas, as we know, is toxic to all of us. So step one, what you need to do is you need to write your appropriate half reactions. So that means we need to go through and figure out with our ions who's being reduced, who's being oxidized. So we have MnO4, that carries a standard -1 charge, is reacting with a chlorine ion. We get Mn2 plus Cl2. We're just looking at those important ions that we know are going to be doing the oxidation reduction. Manganese has a +7, chlorine a -1, manganese 2 plus 2, chlorine a value of 0. Therefore, manganese is going from a +7 to a +2, so it is being reduced. Chlorine is going from a -1 to a 0, so it is being oxidized. Then using 9.2, because we have this little pesky oxygen here, using 9.2, write their appropriate half reactions. I'm not going to go through and do the work with that, but what the resulting answers are is you have MnO4 plus 8 hydrogens plus 5 electrons gives you Mn2 plus 4 waters. You get half Cl2 plus the electrons gives you Cl minus. Because remember, the E theta value is for your reduced value, therefore we're writing our appropriate half reactions to represent the reduction reactions that are taking place. All right, go to table 14, identify the values in which you need. So we have our E cell equals what's being reduced, so our manganese ion minus our E cell for chlorine. Manganese or permanganate on table 14 has a +1.51 value minus a +1.36 value for chlorine, which gives you an overall +0.15 volts. Because that we have that plus sign, this is going to be spontaneous. Now, that nothing here actually tells us what the rate of this reaction is going to be. So we don't know that, but we do know that potassium permanganate will react with hydrochloric acid to create chlorine gas because it's being the oxidized species. And the reduction power of manganate is there in order to, or the reduction power of chlorine is there to help reduce permanganate, so on and so forth. Once again, you could go through and determine your delta G, but be careful when you do that, because as of right now our half reactions do not have the correct bouncing of your electrons. So you would need to fix that for full transfer, but you could calculate your delta G in this particular situation if you needed to.